Hello, welcome to video number 1 of sections 2.9, 2.10. These are the last sections of Unit 2. We'll be talking about derivatives of more specific functions, as well the derivative rule for the operator of division. We call it the quotient rule, just like there was an rule for multiplication, that was the product rule. But just to recap here, Unit 2 has been all about defining the derivative. And I want you to remember that the derivative is always a limit. It's the limit, and I'll write it really quick here. So remember, we said the derivative is really the limit as h approaches 0 of f of x plus h minus f of x all over h, right? Or the alternate would be f prime at c at some value is x approaches c of f of x minus f of c over x minus c. So either way, either version you use, I need you to remember that the derivative is always a limit. However, finding those limits over and over again gets a little tedious because of the process and the algebra involved. And so what we noticed was that there was a pattern. And because there's a pattern, we can create these shortcut rules. And so once we find the shortcut rules, then we can just use the rules and not have to use the limit definition each and every time. So when I come back over here, I want to introduce here the full list of trigonometric derivative shortcut rules. We have already talked about this one and this one. But here I give you without proof, so I'm not going to show you how it's done on this video. I might make some optional videos at the end to show you how we can prove, for example, that the derivative of tangent is secant squared x, or how the derivative of secant x is secant x tangent x. And it turns out that in order to do that, we need the division rule, which we call the quotient rule, because all of these bottom four trig functions can be rewritten as a fraction or a division setup. But anyway, so you're going to need to remember, you're going to need to know off the top of your head that the derivative of sine is cosine. I think we've been practicing that here this week. The derivative of tangent is secant squared, and the derivative of secant x is secant x tangent x. We have to remember those. You should also remember the purple column over here, but let me tell you why I marked them as two different columns. And actually, if you look at the bottom, that's the question that we're going to answer. Do we notice any patterns in the shortcut rules for trig functions? And is there something that might help us remember one column if we knew the other column? And so I'm going to ask you to focus on this purple column with cosine x and cotangent x and cosecant x. And if you heard the first part of every one of those names starts with co, right? Co-function means that it's the partner, if you will, of the one right next to it. So cosine is the partner of sine. Cotangent is the partner of tangent. Cosecant is the partner of secant, right? They're co-functions. But notice that all of their derivatives have negatives. So that's one of the patterns I noticed, because when I look at all the derivatives of the left side, these are all positive derivatives. But the second thing I need you to focus on and maybe notice is that all of the co-function derivatives, which are negative, also follow the format of the derivative rule of its neighbor. Meaning, if I look at cosecant x, the derivative of cosecant x is cosecant cotangent. Well, if you look on the other side, the derivative of secant is secant x tangent x. Even these are just co-functions of each other. And if I look at the next one, or the middle one, the derivative of cotangent x is negative cosecant squared. Well, the derivative of regular tangent is regular secant squared. So what I'm underlining in blue is the same format. And even over here, the derivative of cosine x is negative sine x. The derivative of sine x is cosine x. Those blue underlined parts, notice how they have similar format. What I mean by format is I have a function that's squared. Hey, I have a function that's squared. But more importantly, the functions that are being squared are co-functions. So if you memorize the green column over here and know that the derivative of tangent is secant squared, then you can say the derivative of cotangent is negative cosecant squared. The derivative of secant x is secant x times tangent x. Well, the derivative of cosecant x is negative cosecant cotangent x. So this column, the second column, the co-function derivatives, will always be negative, and they're always going to be the co-functions of whatever the other column is. And so there are some people that just memorize the first side, the left side, and use those patterns to remember the right side. Or you can remember all six. I'll probably in about 2 class meetings, I'll be putting these on the board so that you can kind of see them on a regular basis and start like saving them in your hard drive. We're going to be using them a lot throughout this semester, so I'm sure that you're going to learn them and you'll be using them really quickly by the time we get to December. But this is what we need to do, is start memorizing these trig function shortcut derivative rules, as well as the e to the x rule, the natural log of x rule, the power rule, because we're going to need them in situations like example 1. Okay, example 1 is asking us to find the slope of the line that's tangent, so the slope of the tangent line, to the graph of y. They give me the y equation over here at x equals pi over 6. Okay, so let's break this down. What are we looking for? What's another word for the slope of the line that's tangent to the graph? The slope of the tangent line. This should be something you spit out right away and say, oh, we're looking for the derivative. And the derivative can have different symbols, but I'm going to use the prime notation. We're looking for y prime, and we're looking at y prime at pi over 6. So our goal is to find the derivative of y and then substitute pi over 6, and that's going to get us the slope of the tangent line. All right, so let's find the derivative of this. Oh, I notice we're multiplying. We're multiplying x cubed times tangent x. And that means we have to use a product rule. Whenever we're multiplying 2 or more functions, we have to apply the product rule. So here we go. Let's do y prime. Y prime says, take the derivative of the first, so the derivative of the blue, that would be 3x squared, times the second function, plus take the derivative of the second function. Well, what's the derivative of tangent? Didn't we just write that down? Or wasn't it on the paper? Yes, the derivative of tangent is secant squared. So we're going to write secant squared x times the first function, the way it's written. And that's x to the third. This is the derivative. I didn't set it up. I didn't make my blueprint that I mentioned in the previous videos. I just did the derivative. So the derivative of the first times the second plus the derivative of the second times the first. Great. Now we can substitute the pi over 6. So this finds the derivative function. Now we're going to find the derivative value. So the value at pi over 6, it was pi over 6, yes? Yes. The derivative, oh, we don't want to see news. At pi over 6 is 3 times pi over 6 squared times the tangent of pi over 6 plus the secant squared of pi over 6 times pi over 6 cubed. This is going to get us the answer. Now, 2 things. If you have access to a calculator, type it all in, because you now have the evaluating line here. Like, you've plugged in everything, the calculator will do it. Be careful though, because there is no secant button on the calculator, so you're going to have to write it as a reciprocal, as a flip. So you would write this part, this is secant by the way, you would write this part as 1 over cosine squared pi over 6, right? That's the reciprocal of secant. The reciprocal of secant is cosine. So flip it over. If you don't have a calculator, we're going to try to simplify it as much as possible without getting too crazy about it. Let's see. I'm going to need to square this. So that's going to be 3 pi squared over 36. But we can simplify that. Wait, where did I get the 36? Oh, because I squared the top and I squared the bottom, right? That's how we square fractions. I can simplify the 36 and the 3 and just say, oh, this is really just pi squared over 12, I think. And then over here, there's a plus sign. I'm going to skip the tangent for now, and I'm going to skip the secant for now. Over here, this would be pi to the third over 6 to the third. Do you need to do 6 to the third? You don't, so I'm just going to say 6 to the third. So far, I haven't done too much thinking in terms of evaluating. Now we're going to find tangent of pi over 6, and we're going to find secant squared of pi over 6. So I'm going to come over here, and I'm going to think of the unit circle. We'll pretend that's a unit circle. Maybe better, maybe worse, I don't know. So pi over 6 is the 30-degree line. And at the 30-degree line, we have square root of 3 over 2, comma, 1/2. Why is that important? Because the first number tells you the cosine, the second number tells you the sine. My x-coordinate is attached to the cosine value, the y-coordinate is attached to the sine value. Are we looking for either one of those? No. We're looking for tangent. Well, if you remember, tangent of any angle, including pi over 6, is the y-coordinate over the x-coordinate. But this looks kind of funny because I have fractions within fraction, so we can undo the division by 2, or this denominator, by just multiplying the top by 2. But if I do it on top, I got to do it on the bottom. And so really this becomes 1 over the square root of 3. I would leave it like that, especially if you don't have a calculator and it's a free response, just leave it like that. That's our answer for tangent pi over 6. For secant squared of pi over 6, let me go back over here. I need to remember that secant is the reciprocal, the flip of cosine. But cosine is square root of 3 over 2. So therefore, the flip of that would be 2 over square root of 3. But we didn't want secant pi over 6. We wanted secant squared of pi over 6. Whenever the square, or whenever the power is in between the trig and the angle, that means we're squaring everything. So if I square everything, that means I'm squaring this whole thing. And if I square this whole thing, that means I'm squaring the top and I'm squaring the bottom. So 4/3 is the value of secant squared pi over 6. That's a lot of things I need to remember, right? I need to remember the x and the y coordinate of pi over 6 because I need those values to evaluate trig, sine, cosine, tangent without the use of a calculator, if this is a non-calculator. I also need to know that secant is the reciprocal of cosine. So whatever the answer would have been for cosine, just flip it over. I also need to remember tangent is the y-coordinate over the x-coordinate. So when I come back over here and I say, oh, this is 4/3, I really can't do much with my final answer here except maybe put the first two fractions together, plus maybe put the second two fractions together. And I would just leave it like this and say, hey, this is the slope. There's a multiplication dot there. So this would be the slope if you don't have a calculator. If you did have a calculator, well, then you would have put this in to your calculator, put this into your calculator, and then added everything together. I think the answer is like 0.667 or something. I don't know, something like that. But we can, I'll check it, and then I'll give it to you in the next video. But that's how you would find the slope of the tangent line of this function, this equation, y equals x cubed times tangent x.